here's a complex number, 4 plus I. And I'm going to, the way we represent this graphically is as follows. It looks like the XY plane, except the horizontal axis is going to be called the real axis. The real numbers. So the real part of a complex number falls along the real axis. So this is numbered just like normal. But the vertical axis is called the imaginary axis. Imaginary axis. And it consists of multiples of I. So I've got the I, 2I, 3I, 4I. And same down here, minus I, minus 2I, and so forth. So this is called the complex plane. And often we just, the symbol for complex plane is the symbol for the complex numbers, big C. So where is 4 plus I? Well, it couldn't be easier. 4 plus I is like finding where 4 comma 1 is on a Cartesian plane. So you go over to 4 and you go up to I. It's right here. So this is 4 plus I. All right, let me give you another number. And this one will be, let's make it up here. This number is what? What is that number? Well, it's negative 2 and 3I. So it's minus 2 plus 3I. All right, well, there they are. Now, so it requires 2 dimensions to represent these numbers. So that's why I say they're 2-dimensional numbers. Physicists got pretty excited about this about 200 years ago. They realized that by looking at operations of complex numbers, for example, when you add complex numbers, it mimics the addition of forces in physics. Combine 2 forces. I'll show you that in a minute. So the physicists realized, well, gosh, we can use complex numbers in order to work some physics problems in 2 dimensions. Of course, naturally, the thoughts quickly ran to, well, how can we do this in 3 dimensions? Can we create a 3-dimensional number system? And the logical thing to do is to use, for example, a plus bi plus cj. Introduce yet another number called j. And so there you have 3 components, which means it ought to be a 3-dimensional number. Well, they ran into quite a problem with this, because you can't form a strictly 3-dimensional number system that's viable, that has any kind of meaning to us. It was a very puzzling problem, and physicists and mathematicians kind of stewed over it and wondered, well, what do we do? And finally, around 1840, the great British physicist, William Hamilton, realized, well, we can get around that problem by creating a 4th-dimensional number system, and then only use 3 of those 4 dimensions. This 4th-dimensional system was called the quaternions. And with the quaternions, you had a real part, and you had an I, J, and a K. You might think, well, that's ridiculous. Well, no, it's not. If you play with this stuff, you realize why you need 4 dimensions in order to represent a 3-dimensional number system. All right, so it's a little crazy. He was very excited about this. On a walk with his wife, he carved the quaternions into a tree when he first had discovered them. So he was at that point, instead of carving his wife's initials in the tree, he carved the quaternions. All right, well, that's what any self-respecting nerd would do. Well, now, why 4 dimensions? Well, we go from 2 to the 0 is 1 dimension, 2 to the first is 2 dimensions, 2 to the second is 4 dimensions, and so after that, 2 to the third power would be 8 dimensions. And so it turns out, in order to create multi-dimensional number systems, it appears, at least to me, that you need to go powers of 2. So I haven't delved into that, so I'm not hardly an expert on this. I have seen the quaternions. I really haven't played with them. It turned out the quaternions were very unwieldy. The physicists very soon after discovered vectors, and they went off with vectors and used those ever since. And vectors are sort of a form of this, but they're a lot easier to work with if you're doing physics. All right, so but one thing about the quaternions, just to tell you, that when you multiply two quaternion numbers, the rules of commutivity no longer work. In other words, in the quaternion, this three-dimensional system or four-dimensional system, a times b ends up equal to negative b times a. So more rules of arithmetic break down when you do that. All right, well, anyway, let me kind of wrap this up here and just briefly show you what a vector is. And if I extend from the origin to there with an arrow, and I extend from the origin up to here with an arrow, and then if I pick up either of these, let me say I pick up this vector and slide it over to here without rotating it, without stretching it, then we get, what's that going to be? It's going to be, I want to try to do this precisely. Well, that's close enough. All right. So if I slide this arrow over to here, in other words, that vector, and connect these vectors, then I get a third vector. So it turns out that there's a neat geometry here. This is called an addition of vectors, and this is the resultant vector. So here's kind of how it works. Suppose that you were paddling a canoe across a river, and you were going in this direction, and this represented your speed. And suppose the current is pretty fast, and the current is going in this direction, represented by that speed. So where do you end up going? Well, the current pushes you away off your course, and you end up going in that direction with this speed. And so that's, in a way, that's an addition of forces in physics. It's, I guess it's an addition of velocities, but it's a similar idea using forces acting on objects. So that was why the physicists liked the complex numbers. So it turns out when we add complex numbers, if you add 4 plus I and negative 2 plus 3I, then 4 plus I plus negative 2 plus 3I. You do the natural thing, combine like terms, I get 4 plus negative 2 is 2, I plus 3I is 4I, and if you look up here, this point is the point 2 plus 4I. Exactly. So there we go. Just kind of an introduction to the complex plane. And if you take our trigonometry course here, you'll learn a lot more about complex numbers, because as you can see, there is now an interesting geometry to this. There are angles involved, there are triangles and things like that. So we study complex numbers from a more advanced standpoint in our trigonometry course.